a lot of time talking about stellar nurseries. And in the spirit of the final session of the conference, we're now going to talk about stellar graveyards. So Leah, please take it away with probing the inner regions of black hole accretion disks.
Great, thank you. Hello. Do I need a, I mean, probably need a mic, don't I?
Yeah.
Unless I stay,
pretty well.
Unless I stay here.
Move around maybe.
It puts her on the line if I need help.
Oh.
That's why I think that one doesn't have the puffy thing.
I don't see the puffy thing, indeed.
Yeah, I think there's one right here.
Oh.
Ah.
Yeah.
How's this? Good?
Is it on?
I don't think we ever turned it on. So.
It says off. It is now on. I can't hear a difference.
I think in the back of the room is where it's at here.
Yeah, I could see. Yeah.
All right, please take it away.
Yes, stellar graveyards, great. Hello everybody, my name's Leah. My name tag says Amelia, but the only person who's ever called me that is my 6th grade science teacher, so just call me Leah. Yeah, I'm going to talk about probing the inner regions of black hole accretion disks today. So first I wanted to put up just the canonical spectrum of an active galactic nuclei. Active galactic nuclei, as you might probably know, are known for emitting across the electromagnetic spectrum, from radio all the way up to X-rays and gamma rays. Now what we think AGN are supermassive black holes that are actively accreting material, right? This active accretion gives rise to a disk that is thought to have a multi-temperature black body. As you move in radius, temperature goes up. For a supermassive black hole, that peaks somewhere around 10 to the 5 Kelvin over here. So that's in the UV and optical. That gives you this big blue bump. Other stuff further away gives you the IR bump. But notice I didn't say anything about X-rays. So where do the X-rays come from? The X-rays are not involved in this standard Shakura-Sunyaev thin disk model. And yet they're a defining feature of AGN. Often you can identify AGN by the presence of X-rays. So what's going on here? And this is not a small missing piece of the puzzle. X-rays can comprise up to like 10% of the bolometric luminosity of a system. It turns out that the corona will be very interesting for probing these very inner regions of the accretion disk. If you do things like spectral timing studies on X-rays, or get lucky with like a microlensing event, you can see that these X-rays are coming from the very innermost regions around the black hole. So something like 10 gravitational radii. Gravitational radius is on the scale of an event horizon. So you can see that 10 gravitational radii, that's like, you're going to feel the bending of space-time. You might be able to identify things like the innermost stable circular orbit, which has implications for doing things like measuring black hole spin. All right, so if you're like, I don't care about the inner regions of accretion disk, you should still care about the corona. This is a very weird object. This is a changing look AGN that's been doing stuff for a couple of decades, but not for about a decade, I guess. But what happened recently, this thing has been a radio quiet AGN for a long time. What that means is like there's no appreciable radio luminosity. There's not like a large scale jet or anything like that. That changed a couple of years ago when suddenly the radio emission increased exponentially by a factor of like 60. And so you start to resolve these radio lobes here. And I think now they're like spatially resolved. So this is a jet being launched in real time. But that's radio, not X-rays, so what does that have to do with the corona? Well, at the same time, if you look at the X-rays and you take a Fourier transform, look at this power spectrum, there's a peak at this frequency, about 1 millihertz here. That is a very interesting number because it's approximately, it's comparable to the orbital frequency at the innermost stable circular orbit of the black hole, which is within this like 6 gravitational radii of the black hole. So what we think is happening here, there's something happening in these inner regions of the disk, maybe a magnetic flux inversion event, maybe a magnetic flux eruption that is happening in the corona that's then making it so that the magnetic fields that are vected onto the black hole are vertical or poloidal, which means that you can use the Blanford's-Nyack mechanism to extract rotational energy from the black hole and launch this large-scale jet. So corona is important for these large-scale events as well. But you might notice that this is a pretty long time scale. This is like, if you want to do stuff with that, it's not really a postdoc project. Very good. So instead, I'm going to concentrate the rest of this time on X-ray binaries, specifically black hole binaries. This is a black hole, stellar mass black hole that's accreting off a star. And so these are often discovered when they come from nothing and they become the brightest object on the X-ray sky. And then through the course of weeks to months, so much faster than the AGN, they completely change their spectral shape, and then they disappear again off the sky. So these are very odd objects. What we think is happening is this is kind of one model for what might be happening. The idea is that if basically you're changing the accretion rate onto the black hole. And this model is saying that at high accretion rates, you have a thin kind of Shakura-Sunyaev type disk, like an AGN coming all the way down to the innermost stable circular orbit. That gives you this nice multi-temperature black body, as you see here. Let's ignore this tail. And the idea is that at a different time in this outburst, the disk has moved to larger radii than the innermost stable circular orbit, which means that this inner part is filled by a hot, usually advection-dominated accretion flow. And that flow is like much hotter, and it can lead to things like inverse Compton scattering off of that gas that then gives you a power law from here. And this is often thought to be the corona here. So you might see this is a pretty old model, right? It has a lot of complicated things like dependence of cooling in it. But there's a lot of questions remaining about this, and it hasn't really been explored numerically. So here's some questions on this model. You might say, okay, well, what does this transition look like? Is it actually going to be like you crank up mass accretion rate and the edge marches down? Or you could also imagine that you hit a critical accretion rate and then suddenly everything just collapses down. And that like critical radius or smooth with accretion rate might depend on things like why this transition happens. There's been some recent work with saying that this transition could happen due to magnetic fields. You might imagine that that would give you like a sudden transition in where the disk is truncating. But another possibility is that it's just purely due to gas dynamics, like maybe the protons and electrons can't couple. And this is the thing that hasn't been really looked at before, and that could be important. And so that's what I'm gonna talk about now. So to do this, I do general relativistic magnetohydrodynamics simulations. So I take a fixed space-time, like a spinning black hole with a fixed space-time, put some gas around it, and then let it evolve. The key difference here between what people have previously looked at, usually you assume the gas has one temperature. So the protons and electrons are always tied to each other. That's like really not true, in this hot inner region. You need the protons and electrons to have different temperatures here, versus like that single temperature is a good approximation for that sort of a regime, although I'm going to show it's not actually. So the idea is that the electrons are going to cool because they're radiating, but the protons will only cool if the gas is dense enough that they can exchange energy with the protons. So if you're in this hot inner region, you're going to remain puffy, versus if you have this thin disk in here, then in the body of the disk, the electrons and protons will couple and provide this flatter accretion disk. So let's take a look at what this is showing us. So this is a lower accretion rate thing, kind of analogous to this part down here. You can see this is just like a side snapshot of the accretion flow. It's hot, it's puffy. There's not a lot of density structure. This is time averaged, for example. We crank up the density all the way up to this sort of a thing. You can see there's this body of the disk coming all the way down here. These contours are representing optical depth in white, and then proton-electron contours in blue. So everything in here, the protons and electrons are at that same temperature, which is what you're expecting. But everything above that is not. So okay, I've done the extreme parts here. What about this interesting case of the intermediate case that's so hard to model with simulations? Well, what I find here, this is this intermediate accretion regime, and you can see that there actually is this transition here. So here's the outer cold accretion disk, and then on the inner part here, there's this hot accretion flow here. And it's transitioning at a radius that is slightly larger than the innermost stable circular orbit, which is given by the red lines here. So this is kind of suggesting that this idea could be an interesting thing. And this finding that the disk doesn't always have to extend down to the innermost stable circular orbit could have implications for things like measuring black hole spin, because a lot of spin measurements rely on finding the location of the ISCO, which is in red here. And so this would throw off where you think the ISCO is. Now, if we look at a little bit more quantitatively, so this is a plot of the proton to electron temperature ratio. So again, for like a very low accretion rate, your protons and electrons don't really see each other. They're always at very hot temperatures, as you can see here. But even for this very high accretion rate, so this dashed line is the single temperature regime that the canonical Shakura-Senyev model would have you believe. And we're very well at this tied to this single temperature line until you reach the innermost stable circular orbit. You start plunging into the black hole. The electrons and protons are decoupling even there. And this has implications for where we think particle acceleration might happen inside these black hole accretion systems. And these intermediate accretion rate regimes, again, they're basically single temperature, and then they transition to this 2-temperature regime at radii that are, slightly further in. And this is different from that model I was showing earlier, which is transitioning at like hundreds of RG. This is very close into the black hole, close enough to not significantly affect the radiative efficiency, as you might think. I'm going to skip this for time. But yeah, so then this also has implications for like what is this corona, how is it interacting with the disk? So we can look at where the cooling is coming from in this corona, which in here I'm calling the regions that have 2 temperatures between protons and electrons, and that are optically thin. And you can see that in these, both this is kind of the thin disk model, there's a lot of emission that's happening extended over the body of the accretion disk. And in this transitioning disk between, the thin disk and the thick disk, this emission is spread over the higher layers of the disk. And this could have implications for like the shape of the corona and X-ray polarizations, for example. Okay, so yeah, this was, considering these 2 temperature effects is important to really describe what's happening in the inner regions of accretion disks. It can help you transition from these thin disks to these hot accretion flows with implications for how you measure black hole spin, and also how things like the particles could be accelerated, because this is showing that there's always these regions that are not very well coupled, which is very conducive to having like a power law distribution of electrons that can then potentially explain something like this tail over here, which is the subject of a different talk. And this could have implications for things like those state transitions I was showing, which tend to go through this hysteresis cycle. You might imagine that like one knob you turn is magnetic fields, the other could be something like accretion rate that would lead to transitioning between that thin disk and thick disk moving out. And this could have multi-wavelength emission implications for X-ray binaries as well. You might imagine probing the emission from the corona in, for example, the millimeter, which I talked about last year. So yeah, with that, thank you for a great symposium. This was a lot of fun, and I'm ready for questions.
Okay, we have time for a question. Yeah.
Yeah, it's a nice talk. I'm curious about in the context of tidal disruption events, it's not surprising that we see so few that have any evidence for corona go through a harder X-ray.
Yeah, this is kind of what I was wanting to talk to you about later. Yeah, this is why I was asking you earlier about like maybe it's advection of magnetic field through the disk, because you can imagine like you rip the star apart and then you need some time for like the magnetic field to accumulate and then like reorient and then launch a jet or something like that. I don't know enough about TDEs to say something more concrete than that, other than that these are, steady state simulations. The time scales are very difficult to resolve in simulations, just because like, the scale of a star versus the scale of the event horizon, and then the scale of the gas around the black hole is difficult to resolve. But yeah, we should chat more for sure.
Yeah, one more.
Hi, Leah. Very, very good talk. I understand you can use different accretion rate to explain this transition region, but like, how does the transition actually work? Can you give me an idea of why it's a transition from the solid state to the hard state.
Right, and I guess this is gonna go back again to the separation of scales problem, because kind of the canonical idea for this changing in accretion rate would be something like the companion star is like having some more wind coming through. Maybe there's another alternative is like maybe there's some instability in the disk that allows this to go on. But the idea is that that would come from larger scales than we're able to probe in these simulations, because the orbital separation is so much larger than what I can look at here. But yeah, that is like kind of would be a fun thing to do, would be to kind of include more of these radiation processes and like try to actually recover the spectrum like this to see if you need like the core of the thin disk or not.
All right, let's thank Leah again. You can just send it or give it to her. There he goes. Okay.
Sounds good. How's the sound? Should I put it closer? Is that right? Okay.
All right, next we'll have Cardinal telling us about X-ray flares as probes of active nuclei.
Yes, thank you. And thanks everyone for sticking around. It's been a long and tiring week, but it's been fun. So thanks for the introduction. I'm going to guide you through the type of objects that I've been studying in the last 3 years of my fellowship, actually. And effectively, you can see in this image that we're talking about repeated X-ray flares from the nuclei of galaxies. Just one slide overview as to where the field stands. We have about a dozen of such galaxies, and we have called these events quasi-periodic eruptions because effectively we see X-ray flares, very sharp high-amplitude X-ray flares that repeat from the same galaxy. And this is a collection of a few of these objects. You can see a little bit of diversity in the timing properties, but overall, these are sharp X-ray flares from the nuclei of galaxies, just like pretty much our Milky Way or smaller in size. So we're talking about 10 to the 6 solar mass black holes here. This is, if you want, a cartoonized summary of the ingredients that we are dealing with. We have a black hole of about 10 to the 6, as I mentioned, an accretion disk, compact in size, so quite different from what has been mentioned before. And on top of this, we see these sharp X-ray flares. They don't have a counterpart. We only see them in X-rays. They repeat and evolve on the timescales of hours or days, so really, really fast for the nucleus of a galaxy. And they're, the lifetime is at least a few years, because the ones that we've discovered, most of them are still ongoing. And so, since these timescales are way faster than any timescale that we think an accretion disk should do by itself, maybe some of you won't be surprised that people have been thinking about dynamical timescales to model these objects. And there are various interpretations, but most of them are trying to interpret these X-ray flares as due to the presence of an orbiter on a low eccentricity orbit. So these are the ingredients that we had before. We're adding an orbiter with a high mass ratio compared to the primary. Could be a star orbit core, we don't really know. Sweeping everything under the rug as to what happens when this orbiter passes through the disk. There's a lot of research going on. The idea is that the X-rays would trace the crossing of this object through the disk. Now, this is one of the few interpretations. It's been perhaps the one that a lot of theorists have jumped on, because it's a really cool project and fun idea to work with, but also because this would make these QP flares a precursor or a counterpart to events that LISA or future generation GW detectors should see. And so this is actually a great prospect for a broader community. Since it's my last couple of months before I leave, I thought of looking back and be a little sentimental, and I wanted to be grateful, to the program, because it gives us tons of resources. And in this particular case, the QP field was really, really niche. This is ADS entries as a function of time. The first paper and the first discovery was 2019. I think all observers and theorists here will agree that there's broken power law-like trend in the ADS. And my major result for this talk is that I'm going to bring circumstantial evidence that this corresponds to when I started my fellowship. Unambiguously, I don't think there's any other reason at all. But jokes apart, this program gives us tons of resources, and this is just what happened in the last 3 years. And I think, obviously, to some extent, the program helped the science case of QPs. Before I started, we were about at four QP sources. Now we're more than a dozen. When I started, there was really a handful of people that were working on this for a significant amount of time. And now, in June, we had a dedicated conference of over 80 participants, so this was just in 3 years. 3 years ago, we were in a regime in which we had way more models than QP sources, and now maybe we're converging towards some of the interpretations, the major interpretation, which is the one that I mentioned. It's not unique, but it is perhaps the most dominant in the theoretical works that have been published, and so this is what observers are focusing on testing or ruling out. Now, it's easier said than done, mostly because this model is exquisitely flexible, which makes theorists happy because it never dies. But the problem is that for observers, this makes it really hard to rule it out or confirm it unambiguously. This is a summary of why it's very flexible. If you have an orbiter, effectively you expect all these things to happen. I'm going to guide you through them. The orbit will precess in its plane, side obsession of the orbit. Perhaps the fastest of all these timescales mostly depends only on the black hole mass. If the black hole is spinning, the orbital plane itself would precess over a longer timescale, and this depends on mass and spin. Since we have reasons to believe that these accretion disks are compact and don't necessarily come from a secular accretion event, they're probably not aligned with the spin, and therefore they could also be precessing, and this is a bit of a wild card, unclear what timescales this could be and if they would precess at all. And of course, we expect to see some form of energy losses to shrink this orbit over time, and if it could be obviously gravitational waves, but this could be the subdominant effect. The collisions themselves could be a source of significant energy loss. So all this is happening, and for the most part, we don't have the data quality to test all of these. Effectively, in a summary, for most sources, we have a handful of a few tens of bursts separated by many months over a baseline of a few years, and all these effects have happened in between and sort of makes it hard to compare data. So it's mostly like a data problem, and most of the archival data that we have aren't really made for testing this model. So for a few years, we've tried to change this, and last year, in July 24, we actually took a multi-mission campaign on this source that has all the perfect ingredients for you to try and model it, because it's the easiest by far. It's very regular. You can see here, these X eruptions, how they evolve, or actually how they don't evolve over time. It makes it the perfect source to try and model these with. And we've tried, obviously, we were the first ones, and there are models out there that try to model the evolution of an orbiter through fancy algorithms, but I think this will always find a solution, because the number of parameters is very close to the number of bursts that we have. And so we tried a different approach, which is to be agnostic and try to find whether data tell you whether this system is consistent with anything that walks and talks like an orbit. And we tried something that people have used for decades, which is the O-C, observed minus computed. You can imagine this as a test to see if your system is consistent with periodicity, and if not, if there are coherent residuals or not. Imagine I know approximately what the period is, and I predict in time, I compute in the future when the event is supposed to happen, and then I observed when it actually happens. I compute these residuals, and I see if there's anything interesting there. And by interesting, if you want to see some coherence in this system, if you were to find a sinusoidal residual, this would kind of walk and talk like an orbital phenomenon. So that's the signature we're after. And I'm going to guide you through this plot in a second. This is basically what we've done for this source. Now, the x-axis is the number of events, if you want a counter on the periodic behavior of the source or lack thereof. The y-axis is this time delay. As you can imagine, the horizontal line as if the system were to be exactly periodic, all data points will be on this horizontal line. Any deviation from it tells you if there were delays or anticipation, if it's completely stochastic, or if there is coherence. So what you see here is our data points in blue over a baseline of about a month, which doesn't sound much, but it's pretty much the best you can do if you want to keep a campaign well-defined and contained, and considering there are always some constraints and months-long gaps. And in blue, our model, very agnostic. You just put a couple of sinusoidals. It doesn't have to be an orbit. I guess the main takeaway here is that the system is well described by 3 periods. The period, defined by the cycle, and 2 hierarchical longer ones. And this doesn't know anything about orbits or not. This is just what data seems to suggest. So the agnostic takeaway is that QPs seem to be now finally confirmed as periodic system with some coherent residuals. And for this source in particular, we found 2 hierarchical super periods. I want to be agnostic, and I want to encourage everyone to think as to what could be the reason for such a phenomenon in the nucleus of a galaxy. Obviously, since there is a major model being proposed out there, we've also tried to apply it more quantitatively to the same exact data set. Johin Chakraborty at MIT co-developed a nice code that basically solves the trajectory of a secondary object in the Kerr geodesics. And basically, you can trace each crossing of the disk plane with the data that we have and infer parameters for the source. For instance, the semi-major axis, the eccentricity, and perhaps the most curious is most important one is the black hole mass, which is in agreement with our agnostic analysis and in agreement with the values from the literature. So I guess my summary slide here for a very brief update on QPs is that they are a growing field that started as an exotic type of X-ray transients, and when we started understanding it more, it became appealing to the broader community, the dynamicists, AGN, the AGI community, the gravitational wave community as well. Since a couple of years now, there has been a leading model that suggests that these are due to the interaction of a stellar mass orbiter with the accretion disk of the primary objects. But due to the, data incompleteness and the highly flexible model, we weren't really able to say anything, I would say, conclusive yet. And so we've tried to take data in a way specifically designed to test this model. And what we've obtained is that in a model-independent way, we can say that QPs are periodic with coherent residuals that, again, walks like an orbit and talks like an orbit. It probably is an orbit. And we also applied more sophisticated and physically robust code to fit the data and obtain actually the same results. So this is actually encouraging, and this is perhaps the first time we were able to do it with a well-defined data campaign. And also, as a final point, I doubt the president is online watching the NASA Symposium, but all this was possible mostly with NASA missions, and we should always try to advocate to keep it that way, because people like us and many more actually can benefit from all the nice missions that NASA is launching. Okay, and with this I'm done. Thank you.
Okay, we have time for a question. Leah?
I think an interesting thought, the periodic time period. If I remember right, there's also a QP that seems to have like different amplitudes and different spaces.
Yes.
What is that?
So there's a lot of diversity in the timing. You see some of them are regular, some of them are a lot messier. This system is by far the most regular. I think it's this one here, the one that I applied this dataset to. It has several advantages. It repeats every 2.3 hours, which is by far the shortest. Some of these repeat every few days. So the same campaign couldn't really be done on most of the other sources for, just because it's hard to take infinite data. But once, I think, with this result, we know that the simplest object is actually understandable with that prescription. The most complex ones can be, but they don't have to, we need to verify, can be modified if you add a little bit more frequencies to this problem. And honestly, there are many more than I even mentioned, because disks don't have to be circular, they can be eccentric. This is yet another, but it's much harder to constrain that this is the right model with the complex ones, because data are very hard to interpret, and the model has many more parameters, and you kind of lose track as to what's happening. What we did, we started with the simplest source, and we verified that it actually works. Yeah.
Given this picture, is it straightforward that the shortest period should be most periodic, or is that?
No, it's probably chance. Actually, this one here repeats every 3.7 days, and we don't see it from this one light curve, but it's also quite regular. This also repeats every 2 day-ish. There's a lot more scatter, but it's not a beast that you can't model. So it seems to vary. And also we have a dozen, so I don't know if we can find any meaningful correlation yet. But
so following some of the literature, you're talking about just the observations. The observations show, I believe, that the period is correlated with the energy in the bursts.
yes.
And it goes up.
Yeah.
And I had understood that that's a problem for all of the theoretical models so far. So I'm curious what you think about this. Are we really converging, or is there a new step?
So Dan is referring to the fact that there's been, people have found a correlation between the integrated energy of the bursts and the period, in that the ones that have a longer period have also very high integrated energies. And in this picture here, there is a lot of debate, but effectively there's only so much. Most of the radiated energy comes from the mass that you swipe out of the disk. And there's a limit to this, because you have to have a cross-section from an orbiter to swipe out enough mass from the disk. So some of the ones which have very high integrated energies couldn't be reproduced by an orbiter if we had a stellar mass black hole or a star with its physical size. The workaround that people are focusing on is that, actually it came from simulations before this plot, is that a star will actually puff up and lose mass through its Lagrangian points and sort of form an elongated, more tenuous structure. It's quite convenient, but this increases a lot the cross-section of the orbiter. And also, we're working out whether this is enough for the long period sources. But this seems enough to give you most of them by now, yeah.
All right, thank you very much.
Pleasure to be part of this program.
All right, next we'll have Alex telling us about eccentric supermassive black hole binaries.
Great, thank you very much. It's great to see all of you here today, luggage, backpacks, and all. So this is my second symposium, and so I don't have any sort of heartwarming, touching reflections on the past 3 years, but this is an interesting project to me in that it's the first one I started since becoming a postdoc instead of just dragging things along from grad school. So that's been pretty cool. In case you've been hiding underneath, deep beneath the Earth's crust for the last few years, this is an exciting time to be thinking about supermassive black hole binaries. So very recently, after decades of observations, pulsar timing arrays have constrained and measured the stochastic gravitational wave background. And they've also started putting limits on the anisotropy of that background and on continuous sources, so peaking their heads up above this noise floor as it gets lower and lower. Additionally, Rubin finally has come online, and so it's taking beautiful images. This should be amazing for transient science, active galactic nuclei. And of course, LISA is on the way, and we're looking forward to that. Now, so these black hole binaries form as galaxies merge. They carry with them black holes in their centers. Those form binaries of their own and eventually shrink to smaller and smaller separations that eventually coalesce. And at the very onset of this merger process, the binary is very widely separated. You can resolve it with Irish seeing. And then as the binary shrinks, okay, the separation gets smaller, then you can resolve this binary decently with adaptive optics and with ALMA. But those are still sort of hundreds of parsecs, and the binary isn't really even that tightly bound yet. And so when the binary shrinks to smaller and smaller separations, we just have no hope of resolving it with images. We have to resort to simulations for visualizations or art, and other observational means to try and get at what's actually happening. So looking for signatures of variability in light curves, in spectra, looking for peculiar features in the spectral energy distributions of these objects. But looking forward to pulsar timing arrays and LISA, we should have the ability to maybe identify some multi-messenger sources. When we know from gravitational waves there's some binary there, we can look for different EM signatures that can help us test general relativity, probe cosmology, measure H0, and maybe could help us with this problem of black hole spin inferences. Now, these observations are very challenging, and people have been trying, really since there were time domain optical surveys, to identify binaries from photometric variability. So people did this with CRTS, PTF. Here's an example from Gaia. So some people looked at the Gaia DR3 data and identified about 200 quasi-periodic sources. So that they fit basically damper random walks to the light curves, fit sinusoids, found some where the sinusoidal modulation fit pretty well. So call those binary candidates. And then Cream realized that many of these sources also had ZTF data. So when you look at the Gaia data and tack on ZTF to the two ends, you can see how well that model extrapolates beyond where it was fit. And it turns out that none of the ones that had ZTF data were actually periodic on longer timescales. And unfortunately, this has just plagued these searches for decades. But hopefully with Rubin's deeper observations and higher cadences, we'll be able to get the false positive rate down and actually start identifying some black holes. Now there are other mechanisms people can try. So people have looked at shifts in the broadline regions of AGN over decades. And so the idea here is that most nuclei have, well, a good fraction of AGN have broad emission lines. And so they search for systematic shifts in the centroids of those lines over time, looking for some sort of trend with the orbit of the object. And so here's one that was tracked over about 2.5 decades, give or take, and it seems quite well described by sort of Keplerian radial velocity. So here they can fit a model to it. It fits the data quite well, gets an eccentricity of about 0.65. The main caveat with this is that they haven't quite observed a full orbit yet. So in 5 to 10 years, they'll be able to come back and actually say quite definitively whether or not this is actually a supermassive black hole binary. And so this was using H beta. You can do this with other emission lines as well. So maybe using the blue edge of the iron K alpha line, you might be able to track the motion of these black holes quite nicely as well. So for a theoretical picture, the general features that emerge are that you have a binary that opens up a cavity in the center of this accretion disk thanks to just the strong gravitational interaction. And so very early on, people thought that the torques from this binary would be so strong you might not get any accretion whatsoever. And then in some of the first simulations, actually, so going back to like Artimowicz and Lubo early SPH work, they found that actually the binary can accrete. And now with higher resolution, we can see these miniature accretion disks forming around each of the objects. So every time one of the binary members approaches the pericenter of this eccentric disk, it strips off some material. Some of that gets flung away, carrying off energy and angular momentum from the binary. Other material gets captured, forms these accretion disks, so that naturally modulates the accretion onto the binary on the orbital period. But additionally, so you may be able to see this is not axisymmetric. So the surface density distribution along here varies as the disk itself orbits. And so this will modulate the accretion rate on longer timescales, typically about 4 to 5 binary orbital periods. Now, a lot of this is actually quite generic. So as an example, here is a GRMHD simulation of the binary. And so this is early on before the disk has become fully eccentric, but most of the features are still there. This is a little more turbulent, and this is also a much thicker disk. So unfortunately, in 3D GRMHD, it's just not feasible with computers currently on Earth to simulate thin accretion disks in 3D with a decent amount of physics. And to try and model AGN, supermassive black hole binaries, we really need to think about thin disks. So just to give you some numbers for context, these are just some Shakura-Sinayev type models using slightly more intricate opacities. And the key figure this works. So up here, this is the aspect ratio of the disk, or the scale height divided by radius. So this dotted line is for something accreting at Eddington, and then this is 10th, 100th Eddington. So we're looking at aspect ratios, so h over r, on the order of 10 to the minus 2, 10 to the minus 3. So almost razor-thin disks, and if you get up near Eddington, then maybe a 10th for h over r. Now, if we look at accretion, so this is a nearly circular binary. These are just some time series of the accretion rates onto the primary and secondary over time for different disk thicknesses. So here it's just in terms of the Mach number, which is the inverse of the aspect ratio. And so at the sort of thicker, lower Mach number disks, we see both of these periodicities, this long timescale envelope, as well as this orbital period itself. And as we go to thinner and thinner disks, there's still some of that periodicity, but it's almost all this longer period envelope. Now, that binary is nearly circular. If we go to an eccentric binary, the type of signatures we expect change. So in this case, the accretion is strongly modulated on the orbital period. And as we go to thinner and thinner disks, it does get quite a bit messier. So it's still very strongly modulated on an orbital period, but we do have this envelope that plays a role. We can also see that one object tends to accrete much, much more than the other in all of these cases. Sometimes it switches around in the thinner disks. And this has to do with the eccentricity of the larger accretion disk and also the eccentricity of the binary. So when you have a circular binary, right, you can freely rotate that and the physics doesn't change. But now there's a meaningful difference in orientation between the cavity and the binary itself. So we can see only one of these two is sort of really lit up with accretion. And so one of my collaborators, in the spirit of Halloween, made an animation of this. And so this is showing one snapshot of the surface density every orbit for a few hundred orbits. So you can see as the disk precesses due to the non-Keplerian forces, how this changes the accretion onto one object versus the other. There it goes. All right. Yeah. Okay, so it started all over here. Now it's all over here. There's a little bit of flickering back and forth when it changed over. But yeah, so this might cause some interesting signatures. But generally, for eccentric binaries, we shouldn't expect both to be accreting at the same time. And also the sort of Doppler boosts and modulations you'd get from an eccentric binary are not quite sinusoidal. There's some higher harmonics. Now, if we look at orbital evolution, this problem has been studied quite thoroughly for these thicker disks. And that's kind of nice because we have actual resolved observations we can compare with, and well, lots of galactic data. Okay, not all resolved. But looking at post-AGB binaries, which we heard a lot about, well, the AGBs themselves we heard about this morning. After the AGB stage, a lot of these binaries are observed to have circumbinary accretion disks. And kind of surprisingly, many of them are observed to have substantial eccentricities. So in the earlier stages when the stars swell up, you expect tides to circularize their orbits. So it seems like something is exciting the eccentricities after they've been circularized. And then so these simulations have found that there might be some sort of stable eccentricities around 0 where you can perturb it up to maybe 0.02 or something. And the binary will get damped towards circular. But at this intermediate region, E dot is positive. So if the binary has eccentricity of maybe 0.1 or something, it'll get driven up to about 0.4, 0.45, somewhere around there. And so you have this stable sort of fixed point where at low E, E dot is positive, high eccentricity, E dot is negative. And I was really curious what happens when we extend this to the thin disk conditions we expect for AGN. And going to slightly thinner disks, so about half the thickness, the results don't really change too much. So binaries tend to in-spiral faster. So the top is the rate of change of the semi-major axis. The bottom is the rate of change of eccentricity. And so the picture is pretty much the same. The magnitudes are a bit different for E dot. This fixed point shifts from 0.4125 to 0.4375, whatever. But if we go to thinner disks, it turns out actually just about everything changes. So the binaries in-spiral across the full range. And for every case that I have so far finished simulating, it seems like the eccentricity gets excited upward, pushed towards higher values. So the sort of fixed point, if you extrapolate here, will be about 0.67, give or take. So it seems like for these thinner disks, and this is systematic, I've done a few cases at even thinner disks, it seems like thin disks should drive binaries up towards pretty high eccentricities, 0.6, 0.7, something like that. So we should expect just about all binary AGN to be very eccentric. And a couple implications of that. Here I've just considered a few binaries with sort of mass ranges we expect in pulsar timing arrays and just following their evolution from gas driving and gravitational wave emission that will circularize them later on. And so at early stages, they basically have the steady state eccentricity that we expect, and then they just get circularized. For gravitational waves, if you have a quasi-circular source, at least early in the in-spiral, that'll pretty much emit just a single tone of gravitational waves. But if it's eccentric, we'll emit waves on a number of higher harmonics, and this will move power from low frequencies to higher. And so that if you look at a spectrum from a population of these sources, that will end up depleting your sort of low power at low frequencies and adding power to the high frequencies, leading to sort of an excess at intermediate frequencies, depending on the typical eccentricities. So right now, PTAs have started to probe sort of between sort of 10 to the minus 9, 10 to the minus 8 hertz. And so this should be probed in maybe another 5, 10 years of PTA observations when they start gaining sensitivity to this lower frequency range. Although right now it's sort of ruled out that most binaries have eccentricities of 0.99, give or take. Moving ahead towards LISA, it's basically a similar story. Circularization starts at slightly different masses. One interesting thing here is that as these binaries sweep through the LISA band, they should circularize. And so we should be able to see if they are emitting an ENM, changes in the accretion signatures as they go from the eccentric case to the circular. Because as you might remember, the accretion rate structure we expect is quite different in those two cases. And qualitatively, since LISA should be able to measure the eccentricities of these binaries quite precisely, that may give us some very qualitative handle on what the accretion disk structure is actually like, whether it's very thick, very puffy, or razor thin. And with that, I'd be happy to take a question or two. Thank you.
All right, we have time for maybe one question. Yeah.
Well, okay. Most important question, what is the magic, like a quantification of your data?
No, but bonus points to anyone who recognizes it. I swear it's fair use.
Slightly more serious question. These are hydrodynamic simulations.
Yes, so I forgot to mention, so yeah, because they're razor thin, we are doing this 2D vertically integrated and using an artificial, well, using a Navier-Stokes viscosity to mimic actual turbulence and transport.
Okay.
Great, let's thank Alex again. Next, we have Bing J. Wang telling us about little red dots.
All right. Ready to be the last talk of the whole symposium. Okay. Yes. So little red dots has emerged as a great mystery and also a great discovery in the era of the James Webb Space Telescope. And here I wish to convey some of the excitement to you all. All right. Let's get right to it. So perhaps the most surprising findings in the early Webb imaging is this incredibly, seemingly incredibly massive objects. We call them the universe breakers because in the main interpretations of their papers, we thought they are just galaxies. And when we fit with standard stellar population models, we get supermassive, like 10 to the 11 solar mass, massive galaxies and early universe. To put into context, we can look at figures like this. So there's the redshift versus the stellar mass. In red, this is our sample, assuming a pure stellar population. For reference, this is the mass of a Milky Way, which has evolved quite a little bit, right? And here, this is our sample. They have the mass of Milky Way, but the universe is only a couple 100 million years old, only 3% of current age. This doesn't quite make sense. The other side of debate is, of course, whether they are galaxies or not. If they are, say, black holes, then all the attention is going to indicate. All right. So, and then as more data from Webb become available, we start to find more of those little red dots. They just seem to appear everywhere in every pointings in those public WebD fields. So the number density is very high, which means whatever they are a very important phase in this whole evolution of early galaxies and black holes. If that doesn't convince you they are important, it makes officially to APT. This is the little red dots, so it's with other noble catalogs like IGN, realizations, AGN host galaxies. If you don't know what APT are, I consider it a blast for ignorance, especially this week. Web proposal deadline is next Wednesday. So this is the tool that we use to propose for the web proposals. All right. And then in the early samples, we have some snapshot of the emission lines. What you see here, this is H alpha. We see they are very broad. So this is highly suggestive that we're seeing light from a gas accreting onto a supermassive black hole. So maybe they are just AGNs. What we really need is a full spectrum of those massive galaxy candidates and then see what they really are. Just like a year ago, we finally get the near-spec spectrum of some of the brightest, earliest little red dots, when the universe is only 700 to 800 million years old. This is one of the examples. You can see the cutout here. It looks like a PSF. And this is the near-spec prism spectrum. What's the first thing we notice? Well, those broad Balmer lines are really hard to miss. This is highly suggestive that we are seeing activities of AGN. So are they just all AGNs? Problem solved? Well, there's turns out to be another half of the story, and that turns out to be a more interesting half of the story, which is those spectral breaks. It happens at the Balmer limit, so maybe it did not show that good on this figure. So let me just before that, from this spectrum, it's really surprising that it seems to conform on top of these like broad emission lines, AGNs, old stars at once. So maybe the break does not show very well on this figure. So let me just show you a zooming of the stacked average of 3 brightest little red dots around the Balmer limit region. The individual spectrums are in those color lines. Immediately we see they all have similar shapes and break at the same wavelength, which is the Balmer limit. In black, this is the observed average. And we can also plot a model average, which is shown in red. This is just the average of best fit galaxy spectrum, also normalized. So importantly, the models can also properly interpret this break as a Balmer break. Now, if you don't know what Balmer breaks are, let me just tell you a bit more. Those are produced by the hydrogen absorptions in atmospheres of warmer old stars, typically only visible in stellar populations after star formation ceases, dies off over 100 million years. I cannot stress enough how surprising it is to see the signatures of those stars manifest as Balmer breaks at this redshift, because the age of universe is only a couple 100 million years old, giving very little time to form those involved stellar populations. So this is like the first paper we point out the significance of break, and now it's almost impossible to not talk about breaks in those little red dot papers. So, put in short, we seem to have those two pieces puzzles. One is AGN from the broad emission lines, and this involved stellar populations come from those Balmer breaks. How do we interpret those? In the papers, we derive a set of priors to favor a different range of stellar to AGN contribution. So just to see how informative the data really are. From bottom to top, I'm showing increasing stellar contributions to total light. Let me just start with the simplest model, which is a maximum stellar, basically a galaxy-only fit. This is the simplest we can do. Just fit a stellar population to the spectrum and see what we get. We get a super high stellar mass, 10 to the 11 solar mass, and look at the star formation history. So this is the current age. We're looking back in time along these axes. It formed a lot of stars and then stars shut down. This is what needed to produce this spectral break. I want to emphasize on this star formation histories because it has an interesting connection to another surprising findings from Webb, which is these maximally old quiescent galaxies we find. What we're seeing here, this is a high redshift little red dot, and down here is a quiescent galaxy, so galaxy that stops star formation at redshift above 4.9. This is the star formation history of this galaxy. Again, this is, we're looking back in time. The surprising or the interesting part of this star formation history is it's already have a lot of star formation even above redshift 8. This implies super rapid and efficient star formation. This begs the question, which what are the progenitors of those quiescent galaxies? Because they are forming so many stars at redshift, say 8, 9, then their progenitor should be very bright. So it should be easy to spot. However, we have not identified any of their progenitors of those quiescent galaxies. Now, what if we just plot the star formation histories of those little red dots, assuming a pure galaxy model? This is what we have. This turns out to be the only interpretation that can give sufficient star formation histories to match with these extreme and rapid formation histories for those quiescent galaxies. Taking at face value, if those formation histories are correct, this allows us to draw a very elegant evolutionary narrative. Basically, we can say, well, we found the progenitors of those quiescent galaxies. But there are many outstanding problems in these interpretations. I will just point out the most significant one, is that the stellar mass is uncomfortably high at this redshift. If you are not customized to look at those plots, this stellar mass, what we need to know is just this purple curve. This is the theoretical limit, which means all the baryons in the early halos are converted into stars. This is stringent theoretical limits. Everything above that is a forbidden zone. And with those are the data points if we assume just pure stellar interpretations of little red dots. You see, it gets very uncomfortable. I'm not saying we're breaking the CDM. The precision level is not the same. But again, the star formation is just very early and inefficient. All right, what if we putting AGN into this? That probably can decrease the stellar mass. True. So we derived this host galaxy and AGN composite model where we expand the UV and the Balmer break with the light from host galaxy, which is shown in blue here, and the optical and the mid-infrared from highly dust red and AGN. With it, so because we have beautiful photometric coverage, we can do morphological modelings. And when we do the size measurement, there's an evidence that they are slightly resolved in the UV and purely unresolved, like a point source in the optical to mid-infrared. So this sort of also corroborates with this wavelength dependence contributions of AGN to stellar light. However, this does not solve all the problems. The most surprising one is if they are black holes, they are not normal black holes. To start, they appear to be very massive. So I'm going to quickly go through this. Because usually the black hole mass and stellar mass relationship are very tight. You can imagine the galaxy and the black holes, they grow together, experience their major life events together. So this is a local relation, and this is the black hole mass versus stellar mass if we assume just putting AGN to little red dots. This is like 2 orders of magnitude above the local relations. However, both axes are highly uncertain. Those are derived from 20-year-old scalar relations. There's no reason to believe they are hold at this high redshift. But there are still hints that the black hole mass may be overmassive. All right, and just to emphasize that they are not normal AGNs at this point further, I'm going to show you my favorite example, which is this unusually bright little red dot at redshift 3.1. There. I resisted to call something silly in my paper, but you can see it's super bright, the beautiful PSF here. Because it's so bright, we can measure the size much better. They are totally unresolved at long wavelength filters and slightly extended at short wavelengths. Given that, we use the fiducial model as the host galaxy and AGN composite. This is again the same decomposition. We expand the UV and the break from host galaxy and optical and mid-infrared from AGN. Now, what makes this super interesting is it's at lower redshift, and it's the first one detected in Miri. This is important because this is where we should be seeing a hot dusty torus, this long wavelength range. Just to remind us why we expected to see a hot dusty torus, because typical AGNs, this is also what we use to model those little red dots, they are intrinsically very blue. This is just a median of the SDSS AGNs. But to make them super red, to match the little red dot continuum, we put in ton of dust. Now, by pure energy conservation argument, all those photons in the UV and risk optical are absorbed by the dust, but they have to be emitted somewhere. So in terms of AGNs, we should be seeing a super bright hot dusty torus, a near ubiquitous component in local AGNs. But this is not what we see. It just flattens out. There's no traces of hot dusty torus. This is very weird. Okay. So when we don't have hot dusty torus, and we also look at the Chandra deep field to look for X-rays. They are not detecting X-rays. These are like two tall tales of AGNs, but little red dot just don't have any of those. All right, and there's something, comment, okay, because I do not have the timer. So there's, for the last few minutes, I will just give a brief summary on the things I've been thinking about most recently, which is the ionization mechanisms of little red dots. Because we see little red dots has super high H alpha equivalent width. Under normal photoionization conditions, we can see them as ionizing photon counters. More hydrogen ionizing photons, larger H alpha equivalent width. Now we can put into context and compare with SDSS AGNs. Little red dots overall has a higher H alpha equivalent width. This means we are looking at a lot of hydrogen ionizing photons. And because the ionizing spectrum of AGNs are usually taken as a power law, this means we're looking at intrinsically very blue ionizing spectrum. Well, this is clear predictions for high ionization lines. So we can proceed to look for other high ionization lines to see if this matches with our expectation. If we see such strong H alpha, we should be seeing strong helium-2 as well, because it's just a power law. But we see super weak. Even with a super deep 8-hour medium resolution spectrum, the helium-2 detection is still very marginal. This means whatever the ionization spectrum are, they are not like standard AGNs. In fact, it points out to something that has a peculiar turnover at the helium-2 ionizing potential. If you're familiar with stellar population, it sounds very much like massive stars. Those Wolf-Rayet stars can have those signatures. All right, we can proceed we can proceed to do more physical modelings to push into more exotic parameter space. We identified two of the most important observable signatures. The little red dots had to have low helium-2 equivalent width, but also very red in the rest optical. This is the parameter space we want models to live. However, those are just putting a bunch of fiduciary AGN templates, and none of the points get to this space. So in short, whatever little dots are, they unlikely to have standard AGN accretion depth spectrum. We explored a bunch of options. What can work is we just put in a little bit of stars, massive stars. It can soften ionizing spectrum and also make the continuum a little bit redder. So we can go to this parameter space. All right. So hope I convinced of the rapid progress in this field. And Webb is really reminding us that the universe is still full of surprises. And with the upcoming data, I'm hoping that we can uncover some of those interesting puzzles. With that note, I will stop here. Thank you.
Okay. Are there any questions? Yeah.
So, correct me if I'm wrong, but these overmassive black holes, that's assuming that the line widths are kind of set by the Doppler broadening and the typical, taking the wisdom from low range of AGNs. But there's decent evidence, right, that there should be perhaps some scattering. So if you take into account some reasonable amount of broadening from that, how overmassive are they still very overmassive, or is it perhaps?
Right, so those overmassive black holes are from H alpha. So yes, we assume those scattering relations from reverberation mappings in the local universe. By scattering, you mean electron scattering, all those things? Yes, this is a newly emerged theory that the line broadening can be broadened because of the high density of electrons. So if we think that's correct, true, the black hole mass is gonna decrease significantly. But there's also evidence saying they are not broadened by electron scatter, because they have simple predictions that those gas should be in the nearby area. So when you look at the dispersions of different Balmer emission lines, for example, they should be very similar. but there are papers looking at that. They just show different velocity dispersions.
All right, thank you again, as well as all of you.
Okay, so because of how our schedule has evolved a little bit, this is our last session. So we have lunch still in the cafe after we wrap here, but then we won't reconvene. So once you finish lunch, you can head out. I wanted to say a couple words just to kind of close out to the symposium. Andy and Annetta both had to take off already, so you're stuck with just me as a closing act, and I apologize for that. Thank you guys. This is my first NHFP symposium. Even though these are broadcast publicly, I've never actually thought to call in previous years, to be honest. And I think that was a mistake, because I have to say this was a really impressive summary of all sorts of compelling science taking place across time and wavelength and distance and target mass axes that I do not think about on a regular basis. And you guys, in part due to how competitive and selective this fellowship is, are obviously doing very exciting science. But you are also a very impressive set of science communicators. So these are some of the most well laid out plots and narrative arcs that I have seen in science presentations in many years. And it was a really nice chance to just learn about what is going on across all areas of astrophysics. So give yourselves a round of applause, I think, for giving just a really nice set of talks this week. I want to say a special thank you to our SOC, so Adam, Alex, Nicholas, Justin, Sanskriti, and Sarah for doing a wonderful job of corralling many cats and putting together a really exciting science program. The number of talks that started with, "That was such a great introduction to what I'm about to present," shows just the level of thoughtfulness that went into the order of the presentations this week. We also have them to thank for assembling the science policy panel and the career advice panel, and for leading the excursions on Wednesday afternoon. So thank you guys very much for a wonderful job in organizing. We really appreciate it. And then serious thank yous to all of the local support we have, Gary and Kevin, who have been in the AV booth and providing tech support all week when we continually kind of broke the presentation system. We appreciate the very fast responses for that and for when we had our hybrid presentations. And to Sharita, who was our primary organizer. She is out, I think, right now overseeing the lunch setup, but I encourage you to say thank you to her as you're taking off later this afternoon. And the other folks who have been at the registration desk providing support for us. They are the reason that we can all focus on the nice science results that are being presented instead of running around like chickens with our heads cut off. So thank you very much to everybody in those roles. And then finally, I'm very excited to see what happens in the coming year for all of our fellows who are continuing on. And so again, our next symposium will be at the CFA, the Center for Astrophysics at Harvard in 2026. We've moved it a week earlier, so it will be further away from the JWST deadline, and hopefully that will give people a little more space to breathe as they are presenting and paying attention to the other talks. So that will be September 28th to August 2nd next year. Again, we are excited to see all of you back in person for that. And for the folks finishing between now and then, as NHFP alumni, you have a standing invite to come and hang out, so we encourage you to do so. Thank you to Andy and Annetta for all of the organizing work that went into this. And again, this is the end of this year's symposium, so it was lovely getting to meet those of you I hadn't already met in person. I'm very excited to get to interact with you more over the coming year. And yeah, thank you for a wonderful event, everybody.